So our first lesson in transformations is horizontal and vertical translations. So our goal is to understand how moving a graph up, down, left, or right changes the appearance and the equation. So before we get into this, we're going to learn about intervals. So we know about intervals because we've been doing domain and range, but we've been focusing on doing domain and ranges that look like this. X such that X is between A and B. We can also write it in interval notation, which looks like this. So some key things here, this curved bracket means it's the open interval, means it's not equal to these endpoints. So on a number line, we would have A being our smaller value, B being our bigger value, and we would do everything in between. Closed intervals, so when we're allowed to equal the number, so our domain looks something like this. This is how we write it in interval notation. So you can see here, now we have the square brackets. So this is closed, meaning we can equal those endpoints. So we'd have A here, B here, and we would be anything in between. And just like our domains and ranges before, we can mix and match brackets. So I could equal one side, not equal the other side, not equal one, equal the other. We can also write to infinity. When we're writing to infinity, meaning I go up forever, you can see we always use the curved brackets for infinity. And this is because infinity is a concept, not a number, and we can't equal a concept. So this is how you would say the set of all real numbers from negative infinity to infinity. So domains and ranges might be written in interval notation. They might be written as a set description. You have to be able to kind of recognize both. All right. In this one, we're going to have to know our parent functions. So parent functions are the graphs before we add or subtract or multiply anything to those graphs. So they're the basic functions before we do any transformations. You will always have your calculator, so you can always graph them. But if you have a basic idea what these parent functions look like, it's going to make this unit a lot simpler and smoother when you get all these transformation questions. Okay, so let's look at our basic x squared. So y equals x squared. Graph that. You can see we pass through the origin. Well, 1 squared is 1, 2 squared is 4. Negative 1 squared is 1, negative 2 squared is 4. So we get our lovely parabola shape. Key thing on this one is recognizing when we start at the origin. So our domain is going to be the set of all real numbers. Range, we have to be greater than or equal to 0. Our x-intercept is at 0, 0. Same with our y-intercept. And this guy doesn't have any asymptotes. So remember, asymptotes are those invisible lines that force a break in the graph. They're values of x that aren't allowed in the function. And this graph is allowed to be all values of x, so we don't have any asymptotes. All right, our cubic function, let's see what that looks like as a parent function. So we get this kind of weird little S curve. Again, you can see we pass through the origin. Well, 1 cubed is 1, negative 1 cubed is negative 1. 2 cubed is 8, so I can't actually point that. So we're going to come up here and here. There we go. going to look something like that. So you can see our domain. This time I'm going to write it in interval notation just to switch things up. So our domain is all real numbers. So x belongs to the... Oh. So our domain is going to go from negative infinity to infinity. Our range is going to go from negative infinity to infinity. X-intercept, once again, we just pass right through that origin. And we have no asymptotes. So our square root function So square root is the inverse of a quadratic, which is kind of why we get this half-looking quadratic going to the side here. And once again, third graph that starts here at the origin. And we're going to go this way through. So I just put this here because the square root of 4 is 2, so that's one point that I know is going to be there, so that is what our curve is going to look like. So our domain is going to go from 0 to infinity, or we're going to be greater than or equal to 0. Our range is going to go from 0 to infinity, or y is greater than or equal to 0. And once again, we have an x and y intercept of 0 with no asymptotes. Alright, so our other parent functions, little less familiar with. The first three we've kind of worked with before. So our reciprocal function, we're going to get our hyperbole. So we're going to get, let's get our fraction. We're going to have 1 over x. And there we go. So we do have points here at negative 1 and 1, 1 and 1. And we have this kind of C shape here, or L shape, whatever you want to say. Oh. Okay, so our domain in this one is x is allowed to be anything but 0, because we are not allowed to divide by a 0. X is allowed, or sorry, y is allowed to be anything. Y is allowed to be anything but 0. We have no x-intercept, no y-intercept. And here we have a horizontal asymptote. And when we draw a line horizontally, we cross through the y-axis. So we say our horizontal asymptote is y equals 0, and our vertical asymptote is x equals 0. Alright. 2 more parent functions. Exponential. 2 to the power of x. So it's exponential because now our variable is up in the exponent. And you can see this is a growth one, meaning our graph is heading in the upwards direction. 1 is 2. So we get not touching the x-axis. We are floating above it. There you go. So domain is all real numbers. I do go left and right forever. Our range, as you can see, y needs to be greater than 0. Not greater than or equal to, but greater than 0. We have no x-intercept. Our y-intercept is 0 and 1. And we do have one horizontal asymptote of our x-axis. Y equals 0. All right. And our last graph, which is our absolute value. So if we go in here, absolute value of x, and we graph that, and we get this lovely v. So this is just a linear function that we've said can no longer be negative, which is why we end up with this kind of V shape. So domain x such that x belongs to all reals. Range y such that y is greater than or equal to 0. We have 0, 0, 0, 0. And we have no asymptotes in this case. So you can see a lot of our graphs, our parent functions, kind of have that nice point of the origin, being able to help us determine our transformations. Origin, origin, origin. Our reciprocal functions and exponentials don't have the origin kind of help us, so we would look at the y-intercepts. And for our hyperbole function here, our reciprocal function, we would look at where did these points of 1 and 1 and -1 and -1 go. So knowing these points and knowing these graphs are just going to help you a lot in this unit. Alright, so now let's start manipulating these parent functions. So it says, consider the function f of x equals x squared. So we are defining ourselves a specific function, and our specific function is x squared. So that means we're going to be referring back to this parent function here. It wants us to use the table of values to compare the output values for y equals f of x to y equals f of x plus 2 and y equals f of x minus 2. And with the outputs of -2, -1, 0, 1, and 2. And it wants us to sketch the graphs. All right. So we just have to remember that f of x here, our specific function is x squared. So if I go -2 squared, well, that's going to give me 4. -1 squared, 1, 0 squared, 1 squared, Alright, now this one says that first I have to add 2 to my x value before I square it. So this would be like the function x plus 2 squared. Which I'm going to actually do in a different color here. Alright. So this would look like -2 plus 2 squared. Well, that's going to be 0. So you can see the same output. I have 0 here, I got 0 here. So now my output of 0 is becoming sooner. Now -2 is giving me an output of 0 instead of an output of 4. If I go -1 plus 2, well, that's going to give me 1. And you can see that used to happen when I had a positive 1. Also a -1, but 0 plus 2 squared, that's going to give me 4. 1 plus 2 squared, well, that's 3 squared is going to give me 9. And 2 plus 2 squared is going to give me 16. So if we graph our original function, I'm just going to zoom in a little bit here. We have 0, 0, -1, 1, -2, 4. Of course, we could go -3 and 9 because we know that 3 squared is 9, just to give us a couple more dots to connect. So this is our original function f of x. Now we're going to plot this new one. Now, -2 is 0, -1 is 1, 0 is 4, and if we kind of continue this pattern up, now it looks like we only have half a parabola here. Of course, parabolas are symmetrical, so we can just create the other half of this parabola over here. And then we have our new parabola. So as you can see here, if we compare to our parent function, every single point I moved here just moved over 2 spots. Moved over 2, moved over 2, moved over 2. And this is again because this 0 used to give us an output of 0. But now 2 times or 2 inputs sooner, it's giving me that same output. So because I'm adding this 2, in order to figure out what value of x gives me that same output, I need to subtract 2. I need to adjust by 2. That's why it makes us move to the left. So now we're going to do the same thing with f of x minus 2. And we're going to see what happens with this one. Again, this just means we're going x minus 2 squared. So we're going to have negative 2 plus 2 squared, of course. So that's going to be, negative 2. So this is, of course, going to be negative 2 minus 2 squared. So negative 2 minus 2 is negative 4. Squared is 16. Okay, we're going to have now our input is negative 1 minus 2 squared. That's going to be 9. 0 minus 2 squared is going to equal 4. So again, we're matching inputs. Now to get the input of 4, you can see I'm at my x value of 0. If I go 1 minus 2, well, 1 minus 2 is negative 1 squared is 1. And now we're going to have 2 minus 2 squared is going to equal 0. So you can again see if we're comparing outputs. So it used to be I needed an input of 0 to get an output of 0. In my new function, my adjusted function, now I need an input of 2 to get that same output. So my input is now 2 bigger than it was in my parent function. So this is going to cause our graph to look like this. So when I'm 2, I'm 0. When I'm 1, I'm 1. When I'm 0, I'm 4. And of course, we can extrapolate the other points because we're symmetrical. Here we go, there and there. So now we have the new graph here. So you can see if I compare this one, now I've taken, again, remember we're always comparing to that parent function, the f of x. Now I've taken every point in that parent function and I've moved it 2 to the right in order to get my new function. And this is again because if I'm subtracting 2, I need my input to be 2 greater to get to the same output as before. Because what we're manipulating here is the input, the x values. We want the y values to be the same. So we're going to look at our value of h. How does h affect our graph? The trick with this is the fact that we have a negative here. So when my function looks like this, so let's match colors here. If my function looks like f of x plus h, well, the only reason I can get a plus here, because it always starts with a minus, is if I put a negative h in there, because a negative and negative make a positive. So we can see when h is negative, when h is less than 0, when I had that plus, all of my values moved 2 to the left. So we have what we call a vertical translation. And we say h units left. So if our function looks like this, and it's an f of x minus h, well, that means we put a positive h in there, because the only way I can keep a negative is if I put a positive h in there. So when h is greater than 0, we can see we have a vertical translation h units right. So this is why we kind of say that the inside lies. Because normally when we see a negative, we're like, oh, h is negative means I need to move everything towards the negative. But we have to remember what we did to keep that negative is actually put a positive in there. So when we see a negative, we go towards the right. And when we see a positive, well, the only way we got that positive was putting in a negative, so we go to the left. We also sometimes write this in mapping notation, so this just tells us how to translate each individual point. So, for example, if I took the point from our graph, now let's say one that's not on our graph yet. So if I took the point from our parent function, let's do 416. How I would map it, say using this first transformation when we had f of x plus 2. Well, remember, it's a negative h we're adding there. We're moving everything to the left. So I would say I need to take that x value and I need to minus 2 from it. And my y value is going to stay the same. So with our specific numbers, we would say, okay, I go 4 minus 2, 16. So my new translated point is going to be 2, 16. So this is just a way of looking at it kind of sequentially in your point with our mapping notation. But you have to be careful. Again, if I see a positive, it means I have a negative h value. So that's why we subtract 2 from our x value. So again, in the equation y equals f of x, if I replace x with x minus h, results in a translation of h units right if h is positive, and left is h is negative. But remember, it lies. So when it looks like it's positive, it's going to look like f of x minus h. And this one's going to look like f of x plus h. So this is a your turn, which means pause the video, try it yourself, come back and see how you did. All right, you can see we're still working with the function x squared. It wants us to do two things. It wants us to write the equation, and it wants us to sketch the graph. All right, so it kind of has it in mapping notation here. And in this mapping notation, I can see that this is my h value. So if I put h value into my function, remember our function is f of x minus h. So it would be f of x minus negative 3, which means I would have f of x plus 3. And remember, they gave us a specific function, which is x squared. So we would end in that specific function. So I'm replacing x with x plus 3. and my squared is going to go on the outside. So if it wants us to sketch this graph, it tells us to take all of our x values and subtract 3 from it. So if I take my x value of 0 and subtract 3 from it, I'm going to end up at -3. -1 subtract 3 is -4. If I choose this other point up here, -2 subtract 3 is -5. If I take this point of 1, subtract 3, -2. 2 subtract 3 is 1. So we end up with our new function, moved 3 over to the left. So this is our x plus 3 squared. So mapping notation doesn't lie. You do exactly what mapping notation says. It says take your x and minus 3. But it looks the opposite when we write it in the function. So that's why inside the function it lies. Because you would think, plus 3, I should be moving towards the right. All right, so this other one, again, this here is my h value. So if I go f of x minus h, that's my translation function. I'm going to replace h with my value, which is +2. And again, they gave us a specific function. So it's going to be y equals x minus 2 squared. So we're going to take all of our x values and we're going to add 2 to it. So 0 plus 2 is 2, 1 plus 2 is 3, 2 plus 2, -1 plus 2, and -2 plus 2. So you can see it shifts our entire graph 2 to the right. So again, mapping notation tells the truth. Notation tells the truth. When it's written as a function is when it lies to us. We don't actually subtract 2. We say what x value would give us the same output, so we do the opposite. Okay. So describe how the graph of y equals f of x plus 4 is related to the original parent function. Well, you can see here, I'm adding 4. The only way I could have made this look like I'm adding 4 is if my original, because my original would have said a negative. So we would say the graph of y equals f of x is horizontally translated 4 units left to obtain y equals f of x plus 4. Remember, function notation lies. If I see a positive, it means I'm moving to the left. Okay, so now we're going to look at, instead of putting that transformation inside my function, now I'm going to put it outside my function. So we're still dealing with the same parent function, which is x squared. Oops. Parent function, which is x squared. But now instead of changing my input, I'm going to kind of be changing my output. So what that means, so again, we just have, this is the same thing as saying y equals x squared. -2 squared is 4, 1, 0, 1, 4. This says take my function, my output, and add 3 to it. So all you're going to do is take this and add 3 to it. So that's going to give me 7. Take this, add 3 to it. So that's going to give me 4, 3, 4, 7. So if we graph our parent function, you get really good at graphing these after a while. So again, this one's our parent function. Okay, so now what used to be -2 and 4 is now -2 and 7. What used to be -1 and 1 is now -1 and 4. So we get our new parabola. So you can see all I've done is taken every output and moved it up 3 units. Okay, let's look at our other one. Again, this goes to the original, so we're always going back to the pink column. Now I'm taking 3 away. So 4 minus 3 is 1. 1 minus 3, -2. -3, -2, 1. So this one's now down at -3, -2, 1. And we could find this one. 1, 2, 3 down. 1, 2, 3 down. And we get our new parabola. So you can see all I did was move every output value down 3. So the nice thing about these vertical translations is they don't lie. One, 2, 3. Oh, I have that one pink dot in the wrong spot. This pink dot should be here. There we go. All right. So yeah, outside of our function, when we're not actually manipulating what's happening inside, it tells the truth. So sometimes they write it like this with the y, or the k value, the value that we're adjusting by over by the y. I like to always rewrite it in this form, because this is when it 100% tells the truth. So when I have a k value greater than 0, we have a vertical translation. K units up. And if k is less than 0, we have a vertical translation to call k units down. So in our mapping notation, again, that's just kind of showing you the math that you need to do. So if I had the point 4 and 16, it's telling me that I'm going to keep the x value, which is 4, and I'm going to add k units. So let's say we're doing this plus 3 here. So my new translated point is going to be at 419. I wonder if I can change just this. No, it's going to change the whole thing, so don't worry. So in general, if k is positive, we are moving up. And if k is negative, we're moving down. No tricks there. The only trick they can do, like I said, is if they write it over here, but you're just going to rewrite it like this. Okay, here's another your turn. Pause, try it out. All right, so first our equation wants us to write an equation. Again, it gave us a specific function. So So it says replace y with y minus 4. So we're going to replace y with y minus 4. We're going to solve to get y by itself. So this means a vertical translation 4 up. So we're going to take each point and move it 4 up. Which doesn't give us much room on this graph, but we can get an idea of what this looks like. And this side says replace y with y plus 1. So again, we're replacing the y with y plus 1. Get y by itself. So this one says vertical translation 1 down. So take all your points and move them 1 down. So we get our new graph. So vertical translations are nice because there's no lying. So it says, if the point P2 and negative 3 lies on the graph of y equals f of x, then determine the coordinates of the image point. So image, so this means after the transformation. All right. First I see here that I have the negative 2 on the side with the y, so I'm going to start with isolating y. So y equals f of x plus 8 plus 2. This tells me that I have an h value of negative 8, because remember inside lies, and I have a k value of 2. When you're dealing with just points, this is when your mapping notation really helps. So I'm going to take my original, used to be just x and y, and my mapping notation says I need to take x minus 8 from it, and y I need to add 2. Actually color code that. So we're going to minus 8, add 2. So now we're just going to use the specific point that they gave us. So we have 2, negative 3 was our parent. So now we're going to have 2 minus 8 and negative 3 plus 2. And this is going to give us our new, well, 2 minus 8 is going to be negative 6. Negative 3 plus 2 is negative 1. So this is our image, sometimes labeled as P prime, point of our transformation. So this is when the mapping notation helps, when you're dealing with these coordinates. All right, now they're your turn. Pause, try it, see how you did. All right, so we're dealing with x squared again, and it wants to know, describe how the graph will be related to this. So what are the transformations? And we're gonna sketch. You can just put it into your calculator because I didn't add a graph here and I don't feel like sketching one by hand today. All right, so you can see y is by itself. There's no manipulation here. So I know inside lies. So I think positive to me usually means right. It's lying, so I need to do left. So I have a horizontal translation, which I'm just going to abbreviate HT. Units, horizontal translation 1 unit to the left. And my K value is 3. So we have a vertical translation 3 units up. So that's how the graph is going to change. I take my original x squared function, move everything 1 unit to the left and 3 units up. Okay, and like I said, we can transform any graph. So now it wants us to transform the function of y equals 1 plus x plus 2, 1 over x plus 2. And it wants us to do a vertical translation. So let's color code here. Vertical translation 3 units down. And a horizontal translation 5 units to the right. So this tells me that k equals -3 because we're going down. And it tells me that h equals 3 because we're going right. So if we put this into our transformation function, remember our basic one says x minus h plus k. Well, I know our values of h and k from our function. So y equals f of x minus 3. And then we have to minus 3. That is not right. K equals -3. And we know that h equals 5. So if we put this into our transformation, so y equals f of x minus h plus k. So that's our transformation function. Let's sub in the values we know. So that's going to be x minus 5. And in this case, it's going to subtract 3. And this one, they gave us our specific function. So we're going to replace x. So we're going to replace this x with x minus 5. And then we're going to add a minus 3 on the end. So what that's going to look like is now y equals 1 over. We're replacing x with x minus 5. The original function still had a plus 2. And then we are, of course, taking our k away outside our function. Now we can simplify this. 1 over, well, a -5 plus 2. Because there's nothing being multiplied into the brackets, we can just combine like terms. So we're going to have x minus 3 minus 3. It's going to be our transformed function. All right. Your turn, so pause the video, try it out, see how you do. All right, so we're in mapping notation. So if we're looking horizontally, this tells me that h equals -4, k equals 3, wants me to write the new function, while our transformation function is y equals f of x minus h plus k. If we sub in the values we've discovered from our mapping notation, a negative and a negative, this is going to turn us to a positive h, in this case positive 4, and k plus 3. And that's it. Because they didn't give us a specific function to then sub this in like we did here, we leave it just like that. All right, last example. So what vertical translation, this is key. This tells me that we are only changing our y value. X is going to stay the same because it just wants us to perform a vertical translation. Is applied to y equals the square root of x so that the transformed function passes through the point of 25 and -1. So in order to figure out what this transformation is, we need to figure out where we came from. And that's when this knowing that we're only changing y value comes in handy. That means that this has to stay the same. So if the x value is 25 in my image point, it means it needs to be 25 in my parent function as well. So I can figure out what that is. So first we figure out the original point, when x equals 25. So we got to find the y value when x equals 25. Well, that would be 5. So that means my original point was 25 and 5. And I did something to it, and I got it to 25 and -1. Well, we can see here, to get 5 to -1, I need to move down 6 points or 6 units. So that means I have a vertical translation of 6 units down. And that's it. It just wants to know what is the vertical translation. The vertical translation is 6 units down. If it wanted us to write it in the notation, well, we would say that that's f of x. We would subtract 6. They gave us a specific function, so we'd say y equals the square root of x minus 6. And you can test this out. Square root of 25 is 5. 5 minus 6 is in fact -1. So there you go. So a translation is an operation which causes the graph of the function to shift horizontally or vertically. Doesn't change your shape any, just kind of shifts it around. There you go. Try the homework. Homework key is up on Canvas. Good luck.